Right, this video is on Gibbs free energy, calculating Gibbs free energy in two different methods, and then discussing how delta H, delta S, and delta G are related. Okay, so we've seen Gibbs free energy, but only very quickly in a discussion of spontaneous or non-spontaneous reactions. So basically, Gibbs free energy is a combination of delta H, delta S, and temp that tells us if a reaction is spontaneous. And there is a formula that goes with Gibbs free energy that looks like this, where of course delta G is Gibbs free energy, delta H is enthalpy, T is temp in Kelvin, and S is entropy. And then of course we know from our prior lesson that the sign of delta G tells us info on the spontaneity of that reaction at a particular temperature. And so we've seen before, but just a brief recap. We have three situations. Delta G can be 0, and that is of course an equilibrium situation. Delta G can be less than 0, meaning negative, and so that means the reaction is spontaneous. Or delta G can be greater than 0, positive, which means the reaction is non-spontaneous. And this is super important, okay? So from here, we're going to revisit this formula that we just learned, and we're just going to see that we can calculate delta G if we're given the other three pieces of information. So calculate the standard free energy change for the formation of NO from N2 and O2 at 298 Kelvin, given delta S and delta H. Okay, so really this is just plugging the numbers in. So I know delta H is 180.7 kilojoules. It's positive endothermic, and then minus my temperature of 298 Kelvin times my S, which we have to be careful here because we have a unit issue in that this is in joules and my delta H is in kilojoules. So I'm just going to change this by dividing by 1,000 or moving that decimal point 3 times. So that's going to make my number 0.0247 kilojoules per Kelvin. I could have also changed this to joules, okay, and my delta G would have come out in joules, but that would just be a big number. I prefer to change things to kilojoules. It really doesn't matter what you do. From here, my units, my kelvins cancel out, and I end up then with a kilojoule minus a kilojoule, which is just going to give me a unit of kilojoule. Do the math on my calculator, and I end up with 173.3 kilojoules. So now we have calculated a numerical value for delta G. It comes out positive, which means this reaction is done spontaneous, at least at this temperature. And we know that from the fact that this is a positive value. Okay, so that's how we can use that formula to calculate delta G. We can also use that formula, of course, to calculate, let's say, delta H, but we would have to have been given S, T, and G. So just like any other formula, if I have all the pieces except for one, I can do a little bit of algebra and solve for that missing piece. Okay, so that's one way to calculate delta G. The second way to calculate it is using the standard free energies of formation, which is your chart where it has the values for delta H and delta S and delta G. Okay, so we are going to see that we can use this chart to calculate delta G in a second way. So standard free energies of formation is the free energy change for the formation of a substance from its elements in their standard states. That should sound familiar because it sounds very much like delta H of formation. And just like delta H, but unlike delta S, delta G of formation at standard conditions is 0 for elements in diatomics. Remember, delta S is not, because everything has some amount of entropy. Okay, so the practice here, calculate delta G at standard conditions for this reaction. And then part 2, or B, what's the value of delta G for the reverse reaction? So this is where I need my chart. I think it's called Appendix C. Yeah, because I referred to it down here. So I need my chart of values, and this is where we do products minus reactants. So I guess I should write that up here, that I can calculate delta G at standard conditions by taking the sum of the delta G of formations of my products minus the sum of my reactants. And again, we refer to this as P minus R. We now know we can do this for delta H, delta S, and for delta G. And so that's what it's asking me to do in this formula, or this problem. So delta G for this reaction, P minus R. So I go to my chart. I look all these numbers up, making sure I'm looking at delta G and not the other values. So products first, I have 4 of my PCl3s, and that thing has a value of negative 269.6 kilojoules per mole. But when I multiply that by 4 moles, the moles drop out. That's my only product. Minus my reactants, I have 1 P4, which has a delta G of 24.4. And then if you look it up, but you should say, oh yeah, I have 6 Cl2s, but that's a diatomic. And so it's a delta G of 0. So I do the math, being careful to input my signs correctly, and I end up with this value for delta G, and it's negative, so notice it's spontaneous. And then part B, what's the value of delta G for the reverse reaction? So you could think about this in a couple ways. You could take this reaction, you could flip it, and then you could do the same process. But if you think for just a minute, by flipping it, your products become your reactants become your products, which means these two things would flip. And your value is just going to be the opposite sign of this. So you can do it if you want to, but it's just going to be the opposite sign, just like delta H. So, oh goodness, delta G for the reverse is just going to be positive. And then, of course, it would be non-spontaneous. Okay, so that's how we can use delta G's of formation to figure out delta G for any reaction, as long as it's occurring at standard conditions. That is a lesson for another day, because we do have reactions that occur at non-standard conditions. Okay, so one more problem before we get into talking about how the 3 quantities are related. This says, without using Appendix C, predict whether the value of delta G for this reaction is more or less negative than the value of delta H. And then using Appendix C, calculate delta G. This one's a little bit of an interesting question, and it'll be the first time that we have kind of played this game with talking about signs. Okay, so they're asking me about the value of delta G and whether it's more or less negative. They're not really asking me for a value. They're just asking me, is it going to be more negative or less negative than this value of delta H? So I think what we're playing here is a game with signs. So I have this formula. I know I'm looking for delta G. I know delta H is negative, and that should not surprise me. It's a combustion reaction. So I'm just going to put in a negative sign for delta H. Okay, delta H is negative. And then subtracting from that is T times delta S. Well, T is temperature in Kelvin, which always has to be positive. And then S, in this case, you can kind of determine. I'm going from 6 moles of gas to 3 moles of gas and 4 moles of liquid. So this is definitely a decrease in entropy. S is going to be negative. So when I crunch these signs, so to speak, I have a negative minus, a positive times a negative, which is a negative. And I think easier than thinking about a negative minus a negative is that subtracting a negative is the same as adding a positive. So again, remember the question's asking me what is delta G going to be in comparison to delta H, and delta H is right here. So essentially I'm taking a negative number and I'm adding a positive to it. So what's going to occur is that delta G is going to be less negative than the value of delta H, because I'm essentially taking delta H, which is negative, and adding some positive number to it. It's going to make it a less negative number. So that's my answer for part A. Part B is doing the math and actually kind of confirming that. And so using the appendix C, I can do P minus R to find delta G. So products, I have 3 carbon dioxides as a gas. I have 4 H2Os as a liquid. Make sure you're using the right number. And those are my products. Oops, I'm out of room here. Subtracted from 1 C3H8, that's propane, and 5 H2Os, but I hope by now you know that that is 0. Do my math. And I end up with this for my value of delta G. And we can kind of confirm what we just said. Look, compare delta G to delta H. We said it should be slightly less negative, and it is. Not by a whole lot, but by a little bit. So we were correct in our prediction based on our signs. Okay, the last thing we have to talk about here is temperature and free energy, or delta G. So we know, according to this equation, that delta G varies with temp. And we're going to see that in this chart. So I'm going to look at the 4 combinations of the signs that I can have. And this is a big deal. Okay, and the first one we're going to do is a memorizer. We have to know this. So the first situation is, what if I have a negative delta H and a positive delta S? Okay, what's going to happen to my value of delta G? Well, I will show you this. You don't have to write this because it gets kind of messy, but just to prove it to you. All right, so ready? If H is negative, T will be positive all the time, and S is positive in this case. So I have a negative minus a positive. A way to think about that is that subtracting a positive is the same as adding a negative. And then all of a sudden I have a negative plus a negative. And so there is only one sign that delta G could possibly be, and that is negative. And so this means that this reaction is always spontaneous. Okay, and this is, like I said, a memorizer, because what this means is if I have any reaction, it doesn't matter what it is, any reaction that is exothermic and increases in disorder, delta G will be negative, and the reaction is spontaneous all of the time in that direction. Okay, so if you know that, then you should know that the reverse of those 2 signs is going to give you the opposite value of delta G. Delta G will always be positive, and the reaction will never be spontaneous. Again, you can prove it. I'll prove it real fast. So if delta H is positive and T is positive and S is negative, then a positive times a negative is a negative. And another way to say subtracting a negative is adding a positive. So in this case, you'd have a positive plus a positive, and there's no choice but for delta G to be positive. Okay, so if you know the first situation, you know the second situation. It's the reverse. The next 2 are the delta S and delta H of the same sign. So what if I have a negative and a negative? What if I have a positive and a positive. And perhaps, maybe, as you might guess, this is actually going to depend. It can be either. So let's just do the negative and the negative one. So what if they're both negative? Well, this is a negative minus a positive times a negative, which is a negative. So another way to think about it is adding a positive. And all of a sudden, if you think about this for a minute, you should be able to see, oh, wait, this is going to depend on, is this value larger than this? Be negative. Or is this value larger than this? Delta G would be positive. So in both of these situations, delta G it's going to depend. It might be positive. It could be negative. And so what we do here is we say that it is temperature dependent. Okay, and what we look at, so we'll go back to my example. This was my negative and my negative, delta H and delta S. So if I wanted delta G to be negative, well, then this value would have to be larger than this value, right? The negative would carry the number to be negative. So we say that delta G in this case will come out to be negative, but only when temperature is low, because if temperature is lower, this gives me a smaller value, resulting in a negative delta G. So we say that this is spontaneous at low temp. And as you might guess, the opposite is true for the other one. Now, I would be careful memorizing this whole chart because it's very likely that you could get something backwards. However, this top line, this is a memorizer. Okay, you must know, and this leads into our final part of this discussion. You must know that a negative delta H, a positive delta S will always give me a negative delta G, and the reaction is always spontaneous. Okay, that's really important. The very last topic is something called the driving force toward spontaneity. Okay, and so this is a discussion of that a spontaneous reaction must have a driving force that pushes this reaction toward being spontaneous. Okay, it can be delta H, delta S, or both of them. So our topic now is what values of these quantities favor a spontaneous reaction. And for delta H, it's negative. And for delta S, it's positive. Well, that's the same thing as that first row of the table that we said, right? Remember, if you have both of those criteria, you have a spontaneous reaction. So in order for any reaction to be spontaneous, it must contain at least a negative delta H, or at least a positive delta S, or both. Okay, and then whatever of those it contains is what is said to be the driving force of the reaction. So we're looking at which quantity is it who's responsible for pushing this reaction toward being spontaneous. That's identified as the driving force. So let me make up an example real quick. Let's say we know that we have a reaction and we know it's spontaneous. And I know that delta S is negative. And our discussion now becomes, what do I know about delta H? Okay, so you can actually play the sign game with the formula, but there's a slightly easier way to think about this, okay? And this is the easier way. It's to figure out the driving force of the reaction, because see, I know this reaction is spontaneous. And if it's spontaneous, it has to have a driving force, at least one, okay? So look at delta S, right? Well, is delta S is negative. Is that the value of delta S that drives a reaction toward being spontaneous? No. So delta S is not the driving force, which means in order for this reaction to be spontaneous, it has to have at least one driving force. So it must be delta H. And the sign for delta H that pushes a reaction toward being spontaneous is negative. So we know without a doubt that delta H must be negative. and it is referred to as the driving force of the reaction. Okay, let's do one more example, and I'm going to give you the same reaction we saw a minute ago. I'm going to tell you that this reaction is spontaneous. And I want to know what the driving force of the reaction is. So it has to be something, right? It's either enthalpy, entropy, or both. So we have to think about this. This is a combustion reaction, and delta H is negative. We can also predict delta S. It's an all-gas reaction, so I look at moles. I have 6 moles of reactants, and I have 7 moles of products. Entropy will increase. Okay, so delta H is negative. Hey, that's the one that pushes it toward being spontaneous. Enthalpy is the driving force. But guess what? Delta S is positive, which means entropy is also the driving force. Who's the driving force? Both delta H and delta S. This is a very big topic, and the AP exam loves to ask you, well, which quantity is the driving force in this reaction? Is it enthalpy driven or is it entropy driven? And that's how you have to think about it.